Depth first traversal is another traversal mechanism used on trees and graphs. The depth first search or traversal goes in deep in each branch of the data structure before moving to explore other branch. So let's just illustrate this. If you look at the blue annotations here, the sequences 1, 2, 3, traversal happens from the root level and it goes from top all the way to the bottom towards the left side of the tree. Once done, it bubbles up back into the root. As it kind of goes back to the root, it collects the other siblings along the way. So this is the subtree we're talking about. So the entire traversal looks like this. Goes down to the bottom of the tree, back up again, going back to the root. At the end of the very first subtree, it reaches the leaf number 1, kind of the dead end. There's no more to traverse into. As it goes down again, and maybe this time it reaches leaf number 2, back up again, right? Going back down, going up, and it goes back to the R. And then maybe this time it goes all the way down to another branch. And this leaf here is leaf number 3. It traverses back through the same subtree into the root. This is what the mechanism is. So if you look at this illustration here, 1, 2, 3, it goes into the leftmost, right? Subtree and then back. So A, B, C, T here is one subtree. And this is all the way on the left side. F is a middle tree, right in the middle. So it goes back down and then back up again. And there's nothing to collect. There's no siblings or anything else. It goes into 6, 7, 8. And then this subtree has no other branches. So it simply just go back up. And as it go back up, it doesn't recount the node that has already been visited. You're basically just recounting the new ones as you go. So this entire breadth first traversal is vertical, right? As opposed to BFT is all horizontal, right? Going back and then horizontal, going back and horizontal. This is depth first traversal. Let's look at the specific algorithms that constitutes this DFT. Sometimes, people refer to the DFT as a depth first search or DFS. Search is about looking for a specific target. In traversal, there's no target in general. Lots of time, people kind of take one as the meaning for the other. So we're not going to strictly enforce the use of terminologies in this course. You can call it DFS, DFT, doesn't matter. Let's move on to the specific algorithm. If you recall for breadth first search, we're using Q. In depth first search, we're using what's called stack. Breadth first search kind of stores this information inside a queue, first in, first out. The search itself kind of relies on this queue's nature of deferring the decision towards the very end, meaning the first person goes in, gets enqueued. Whoever enters towards the end is the last to be looked at. In depth first search, we kind of want B to make the first decision, right? Because we want to go down here immediately. So we can't just wait until, hey, everyone has done their part, come back to B. This means we have to use last in, first out. Because you want B's branch, right, this entire branch to be executed first. You kind of have to put B on top of F, then F has to be on top of X. It's kind of like this. In the beginning, we start up with an empty data structure. We have to have A on the bottom, and that's what root is. At the end, we get down to the next level. Root is level number 0. So depth requires B's subtree to be evaluated first. Let's go back and reason this out. Your entire stack, at some point, is going to have something like this. By the time you get X, F, and B in there, your A is already gone. This is kind of the nature of pseudocode here. Instantiate a stack of nodes. The root is not null, and then we go back and we start pushing it. So stack is push and pop. It's not enqueue and dequeue. First of all, this is a typo. This should be stack. This is one operation. Java doesn't have top here. This is strictly possible with the author's implementation of their own stack interface. We want B to be on top. So the lookup, push children to node and do a visitation. The visitation has to be from right to left. In this case, instead of going in the queue fashion where we have left to right, visiting each node has to start with X and then F and B, because that way we can put B on top. The same mechanism ensues when you're done visiting all of the nodes and the stack has all of the information, stack is not empty, and they keep on popping the top one. The top one is B, and then you visit this one. By the time you're done, after you pop B, what happens? Well, B is going to have two descendants, right? And you're going to put T on top of B and then C on top of T. Notice that we haven't really touched F. We haven't touched X yet, right? So it's just C, T, B is gone, F, X. So that's kind of the iterations that we're looking at. By the time you're through to the very end, there's no more children. There's no more to visit, and then you go back to stack empty, and it goes into a different subtree at that level, and then different subtree after that. And then just keeps on going until you're completely through. There's no more children or no more child to visit.